In this lesson, we're going to start by looking at the derivatives of exponential functions. Given a function like a to the power of x, by the end of this lesson, you're going to be able to find the slope of its tangent at any x value you like. Or in other words, if I gave you a function like 3 to the power of x, you might want to know its derivative function at any x value you like. Aside from just giving you a new function that you know how to differentiate, this discussion is also going to teach us about this number e. I'm going to explain to you why e is one of the most important numbers in all of mathematics. But without further ado, this is a lesson on the derivatives of exponential functions. So as we said, throughout this lesson, I want to investigate how to differentiate f of x equals a to the power of x. I want you to remember that a can be basically any positive number you like. So to keep track of which a we're talking about, I've also written a as a subscript on the function name. So to actually figure out how to differentiate this function, I'm going to begin by looking at a particular version of this function. So instead of looking at a to the power of x, let's look at 2 to the power of x. In order to graph 2 to the power of x, I want you to remember that when x equals 0, a to the power of 0 must be 1, so it has to go through here. Also, when x equals 1, then 2 to the power of 1 is just 2, so it also must go through here. And then the resulting curve joins these 2 points and then continues growing forever. Now in order to actually find the derivative, we want to try finding it around a particular place. So we're going to try to find the derivative when x equals 1. Now there's nothing special about x equals 1, because the argument I'm about to make is going to generalize to basically any point. So let's just try at x equals 1. Now, because we're looking at a new function again, we're going to need to invoke the first principles definition of differentiation. So if I wanted the derivative of f2 of x, then I'm going to need to write it like this. So if we want the derivative of 2 to the power of x, then we need to evaluate this whole limit over here for the case when f of x equals 2 to the power of x. Remember, the whole idea of this limit is that we're going to take a small step in x, which we call change in x, and then we're going to try to find the corresponding change in y. This numerator over here is the change in y, and the denominator is the change in x. So change in y on change in x gives us the gradients. And then we want to take the limit as change in x approaches 0, so that we can get as close as possible to the true tangent line. If any of this doesn't ring a bell to you, you should definitely watch my video where I introduce the first principles definition of differentiation. But as I said, for now we're going to focus all of our attention to finding the derivative at x equals 1. So where I'm going to start is I'm going to replace all of these x's for 1's. By doing this, we're going to find the value of f-2 of 1, and that gives us the derivative of 2 to the power of x at x equals 1. Now, before we try finding the true derivative, how about we start by trying to approximate it first? So instead of letting change in x approach 0, what I'm going to do is I'm just going to pick a really small value for a change in x. So let me just pick a small value at random. Let's let change in x be 0.0001. If that's the case, then we're just approximating the derivative, so the limit is going to go away. Then, instead of writing 1 plus 0.0001, how about we just write it as 1.0001? We don't really need this plus here. Now at this point, I hope you can roughly see why this is actually going to give us the correct gradient. We're trying to find f2 of 1.001, which is going to be this height roughly here. And then we're going to subtract f2 of 1, which is this height. That roughly gives us the change in y. Then we divide this by 0.001, which is the change in x. So to get our approximation, let's just replace f2 of 1.001 for 2 to the power of x, where x is 1.001. So because f2 of 1.001 is just 2 to the power of 1.001, we can go ahead and replace it. And then by the same logic, f2 of 1 is going to just be the same thing as 2 to the power of 1. But 2 to the power of 1 is just 2, so I'm going to replace this whole thing for 2. It also occurred to me while I was writing that I might have accidentally forgot a 0 here. You need to make sure that you match the number of zeros up top with the number of zeros down the bottom. Otherwise, none of this is going to work. But now, after all of this work, we finally have something that we can type directly into a calculator. So at this point, we've discovered that the derivative of 2 to the power of x at x equals 1 is approximately equal to 1.38634. Let me go ahead and actually draw this directly onto the diagram. So notice that when x equals 1, the height is of course going to be 2, but then the slope is going to be 1.38. I've drawn it with this triangle though, because 1.38 is kind of like a gradient, and a gradient is a rise over a run. So if you run by 1, then you have to rise by 1.38 to stay on this tangent over here. So now that we have a useful approximation for the derivative of 2 to the power of x when x equals 1, then we can also repeat this approximation for any other base other than 2. So let's go ahead and redraw this exact same graph, but instead of drawing 2 to the power of x, let's draw 3 to the power of x. So what I have here is the graph of 3 to the power of x, and you can see that because when x equals 1, y is equal to 3. We can find the derivative of f3 of x just by repeating the same procedure we had over here. The only difference is going to be that these 2's become 3's. And then we can just go ahead and ask the calculator what this is equal to. So this time, we notice that the derivative of f of 3 at x equals 1 is equal to 3.29601, which I'll also go ahead and draw directly onto this diagram. Now at this point, we've come to a really important part of our journey, and for you to get the most out of this, I really recommend you pause now for a few moments and try to look at these two graphs really carefully. Hidden somewhere between these two graphs, there's a really important observation that needs to be made. There's a relationship between the outputs of the functions and their derivatives. So I'd like you to pause now and try to figure out what that relationship is. So at this point, I'm going to assume that you've thought about it and you've unpaused. But the thing I wanted you to see is that the output of the function here is 2, and the derivative is 1.38, so the derivative is smaller than the function's output. But in this case over here, the derivative is actually larger than the output of the function. There's also a neat visual way to see this as well. I want you to notice that the tangent for 2 to the power of x crosses above the line, but the tangent for 3 to the power of x crosses below the line. This happens because the base of this triangle is 1, and this distance is also 1, so this height over here is smaller than the total height over here. So when the base is 2, the derivative ends up smaller than the actual function, but when the base is 3, the derivative ends up larger. So that means there's some number, somewhere between 2 and 3, where the derivative exactly equals the output of the function. So I've made this statement one more time. I've said that there must be some base a whose output of the function is totally equal to the value of the derivative at x equals 1. So as we already saw, when a equals 2, f dash a evaluated at 1 is equal to 1.38. And when a equals 3, f dash of a is the same thing as 3.30. I've also marked the important information. When a is equal to 2, we can see that the value is too small. And when it's equal to 3, the value is too large. So somewhere between 2 and 3, the true value belongs. Now, there's going to be quite a few numbers that need to be subbed into the calculator now. But I want you to realize that all we're going to do is we're going to use this over here. For example, I'm going to try 2.5. So at 2.5, rather than typing 3, you just type 2.5. So when a equals 2.5, we can see that its derivative is approximately 2.29. So this derivative is also smaller than the base. So this is smaller, and the range is actually between here and here. Now, in the interest of saving some time, I'm not going to keep typing all of these values into the calculator, but I really suggest you keep pausing and checking my values, just to make sure I'm not making any mistakes. So next we need to try some value between 2.5 and 3. So how about we try 2.8? Well, if we sub 2.8 into the calculator, the answer is going to be 2.88. And because 2.88 is bigger than 2.8, then we've shrunk the range to be a number between 2.5 and 2.8. Now at this point, I'm going to try 2.7. If we sub 2.7 into the calculator, we get 2.68. And because 2.7 is actually larger than 2.68, then we've shrunk the range to be between 2.7 and 2.8. So at this point, you should be pretty confident that the first digit of our number is 2, and the second digit of our number must be 7, because the answer is somewhere between 7 and 8. But we can go further by actually expanding out this number line and continuing. Now, the longer we keep continuing this process, the closer we're going to get to our special base of a. But it turns out we could technically do this process forever, and we would never exactly get to the value of a. That's my way of telling you that the value a we're looking for is a real number, and you could just continue this process to get more digits, but you could never find it exactly. But either way, if we found the value at 2.75, that would equal 2.78 when we plugged it in to our calculator. Now, because the value is larger, we've shrunk our bounds to be between 2.7 and 2.75. Now, if I want to continue this process, I'm going to need a little bit more precision. So if I tried finding the value at 2.72, the answer would be 2.721. And of course, that means our bounds are now between 2.7 and 2.72. And now for one final evaluation. Let's try 2.71. If you plug in 2.71, you are going to get 2.70. And that means that our bounds are between 2.71 and 2.72. So therefore, the first three digits of our special base are 2.71, because the value is somewhere between 2.71 and 2.72. Now, you may or may not have some alarms ringing in your head. You might actually recognize that the value, who starts with 2.71, is a special number we call e. So this special number, even if you don't recognize it, is called Euler's number, and it is one of the most important numbers in mathematics. In a sense, you can think of Euler's number as the only number whose slope is exactly equal to itself. It also turns out that there's nothing special about drawing this picture for when x equals 1. If you drew the same picture for x equals 2, you would notice that the slope and the function value are going to be exactly the same as long as the base is equal to the number e. So putting this in other terms, if we allow a to be equal to this number, which we call e, then we're going to find that the derivative of e to the power of x is equal to itself. So the derivative of e to the x is equal to e to the x. So this brings us to this really important fact here. We can see that the derivative of e to the power of x is totally equal to e to the power of x. That's only true when a is equal to e. But we came here in the first place to find the derivative of a to the power of x. It's lovely that we have the derivative of e to the power of x, but we want to be able to use any base we like. So I'm going to show you a way that we can do that as well. But I'm going to show you that you can actually differentiate any function you like just by knowing the derivative of e. And there's a very cool trick that you can use to do that. So let me pull out an example and I'll show you how. So we know how to differentiate e to the power of x. But how do we differentiate e to the power of 3x? Well, to do that, we need to get a little bit clever. I want you to remember that we can write e to the power of 3x by the index laws as e to the power of x times 3. And now, if we want to differentiate e to the power of x all to the power of 3, we just have to realize that there's a function inside of another function. And as you should know, anytime you want to differentiate a function inside of another function, you need to use the chain rule. So that involves differentiating the outer function in terms of the inner function, which I've drawn here, and then you've got to multiply by the derivative of the inner function, which I've drawn over here. So if we want to differentiate the outer function, you just cover up this e to the x, and then you just use the bring the power down rule. You bring the power down, which is going to give you 3 times whatever's in here, all to the power of 2. But then after this, we have to multiply by the derivative of the inside. Now, the derivative of e to the power of x, as we already know, is just equal to e to the power of x. So we're just going to copy this right out here. And now at this stage, I want you to notice that we have e to the power of x all squared, all times e to the power of x. So of course you could rewrite this as e to the power of x all cubed. But then of course, you could also rewrite this as e to the power of 3x again, because this bracket over here, by the index law, can just disappear. So at this point, we can see that if f of x equals e to the power of 3x, then the derivative is just going to be 3 times e to the power of 3x. Now, this works for any power you like. If this was a 7, then this would also be a 7. And no matter what, you're always going to see this pattern repeating itself. But rather than using the chain rule like this, there is actually one more way to look at this. So the other way to look at this, rather than using the index laws, is to imagine that the e is actually the function on the outside, and then 3x is the function inside of it. And then the chain rule just works exactly the same way. You differentiate the outside in terms of the inside, and then you multiply by the derivative of the inside. Now, I wrote this in the opposite order, just so it's going to look exactly like this. But the first thing we do is we just differentiate e to the power of 3x, covering up the 3x. Well, we know that e differentiates to itself, so we're going to copy this directly into here. But then to finish this off, we just need to differentiate the inside. So the derivative of 3 times x is, of course, just equal to 3. So I want you to notice that this and this down here are exactly the same, just as we expected them to be. But then if that's the case, then this derivative over here also follows the chain rule. So let me go ahead and copy this over here down there. So I didn't draw a box on the outside, but I said that e to the power of any function we like is always going to equal e to the power of the same function times the derivative of the function. In other words, it always follows the chain rule. And that makes sense because after all, the chain rule is supposed to work for any function, so why should it break down for this one? Armed with this knowledge over here, it's actually possible to differentiate any base we like. So let's go ahead and do that as well. So in order to differentiate 2 to the power of x, which is equal to g of x, we're going to need to use a special trick that I talked about in my logarithm videos. And that's the fact that logarithms and exponentials cancel each other. So we can use this to say that the number 2 is the same thing as e to the power of the log base e of 2. In other words, this e and this log cancel each other out to give you back the 2. But if that's the case, then I can go ahead and replace this 2 for this whole expression over here. So let me go ahead and do that. Now initially this looks like things got way worse, but bear with me for just a moment. I want you to notice that at the top, using the index laws, I can rewrite this as e to the power of log e2 all times x. And you need to be a bit careful about a few things here. I want you to realize that this log e2 is just a real number. You can calculate it with a calculator. Also, I want you to realize that this x is not subbed into the log, so do not imagine this x inside the log. But then we can just see that this is just a function inside of another function, just like we had in the last two examples. So just like before, to differentiate this, we differentiate the outer function in terms of the inner function, and then we multiply by the derivative of the inner function. Now e to the x differentiates to itself, so we're going to just copy this down here, just like we did before. And then we just differentiate the inner function. Well, I want you to realize that the inner function is just a constant times x, so the derivative of any constant times x is just going to be the constant. For example, the derivative of 2x is just 2. So now at this point we have the derivative of 2 to the power of x without really needing to look at first principles. The derivative of 2 to the power of x is the same thing as the log base e of 2 all times e to the power of the log base e of 2x. And to be clear, this x is not subbed in to this log base e. However, there is one further simplification that we can make. I want you to notice that this is the same thing as this, which is the same thing as g of x. And g of x is the same thing as 2 to the power of x. So this whole thing must be the same thing as 2 to the power of x. So we can see that the derivative of 2 to the power of x is the same thing as 2 to the power of x times the log base e of 2. That was the missing part here. We had to remember to multiply by the log base e of 2. But of course, there's no reason this should only work for a base of 2. In fact, it works for any base. So we can say that the derivative of a to the power of x is always going to be the log base e of a times a to the power of x. This rule works no matter what the base is. It even works for e. If we allow a to be equal to the number e, then we have the log base e of e, and of course that's 1. And then we multiply this by e to the power of x. So in the derivative of e to the power of x, the log base a of a doesn't show up, because that's just equal to 1 in that case. But to show you something interesting about this, let's evaluate the derivative at x equals 2, so we can compare it to the value we got before. So when we look at the calculator, the answer we get is 1.3862, and that's the same as the 1.38 that we got before. So I want you to notice that you can now differentiate any function that's an exponential function and for any base. But at this point, I'd just like to summarize the lesson. In this lesson, I showed you how to find the derivatives of any exponential function in the form a to the power of x. We started by approximating 2 to the power of x and 3 to the power of x. We saw that the number that came out of 2 to the power of x was larger than its derivative, but the number that came out of 3 to the power of x was actually smaller than its derivative. Using this information, we were able to infer that there was some number in between 2 and 3 whose derivative was equal to itself. This special number is e, so we can see that e to the power of x, when differentiated, still equals e to the power of x. By looking at an example, we were able to show that e to the power of x does indeed follow the chain rule. And then because it follows the chain rule, we were able to show that the derivative of a to the power of x is the log base c of a times a to the power of x. So at this point, I think it's fair to say that you know how to differentiate fairly simple functions that involve exponentials. But in the next lesson, I'm going to show you how to differentiate much more complicated functions that feature exponentials. So tune in for the next lesson where we talk about differentiating harder exponentials. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.